Hello, today we talk about the time-dependent perturbation theory, which is we want to find the solution to the Schroedinger equation for this Hamiltonian, which can be written like a time-independent Hamiltonian, of which we can find the eigenvalues, plus a perturbation term which will depend on time. Now, I did a video recently about the time-independent perturbation theory, where W was equal to h1 times lambda. Lambda was small and h1 did not depend on time. Here W of t is a small perturbation, but it depends on time. And when we solved this problem with the perturbation independent on time, we used the time-independent Schroedinger equation, right? We found an approximate solution to this equation, this eigenvalue equation. Now, we can't do that with a time-dependent Hamiltonian because the Schroedinger equation in that case can't be factorized to this eigenvalue equation. So we must use another method. In particular, we're going to use a particular picture of quantum mechanics, which is particularly useful when solving this kind of problem. But first, let's review the two main pictures of quantum mechanics: the Schrödinger picture and the Heisenberg picture. The most direct picture of quantum mechanics is the Schrödinger picture. In this picture, we have time-dependent states which evolve on time with the Schrödinger equation, IH bar and H of psi of t. These evolved states can be viewed as an evolution of a previous state at time t0 through a matrix of evolution u of t minus t0. This is a unitary matrix, so its inverse is u dagger, the transpose conjugate, and u dagger u undoes the time evolution, so it gives the identity matrix. So when the Hamiltonian H does not depend on time, this Schrödinger equation can be factorized like this, and you will take a very simple exponential form. We have u of t minus t0 equals the exponential of I h t minus t0 divided by h bar. So this is the Schrödinger picture. We have these states which evolve with the Schrödinger equation, but in quantum mechanics we never measure states directly. In fact, in quantum mechanics we have states and observables, and we will have random results after measuring an observable, and we can write the expected value of an observable. Let's say we have an observable A, and the observable, the average value of the observable, the expected value of the observable can be written with this scalar product, this bracket product, psi A psi. So we never measure psi and the observable themselves directly. So we can have different pictures, different descriptions of quantum mechanics by changing the way we describe states and observables, as long as these products are the same. For example, I can send psi to another representation of psi through a unitary transformation to have another picture of quantum mechanics. So the bra vector will be transformed with this u dagger, and then we will get this, and and In order for this product to remain the same, we must add u and u dagger here, so we must send a, also the observable a to u and u dagger, because u dagger u is the identity, so this product will be equal to this product. So this picture of quantum mechanics, when psi is sent to u psi and a is sent to u, a u dagger, with u being an arbitrary unitary transformation, is also a valid picture of quantum mechanics. So for each unitary transformation we have infinite equivalent pictures of quantum mechanics. So this is the expectation value written in the Schroedinger picture notation, and the second famous picture is the Heisenberg picture. In the Heisenberg picture we have time-independent states, because in the Heisenberg picture the matrix U we are going to use, which sends psi of t to psi of t u, will be the evolution matrix. So u dagger undoes the evolution, so this will be c of t0, and it does not depend on time, and this will be the bra c of t0, right, because the cats are undone by u dagger and the bras are undone by u. And here we have the expectation, the observable in the Heisenberg notation picture. U dagger t minus t0, a u t minus t0, where u is the time evolution matrix. So, Schrödinger picture, time dependent states, and the observable can be either time dependent or time independent, but if it is time independent, it will be anyway time dependent in the Heisenberg picture, but in the Heisenberg picture we will always have time independent states. So states in the Heisenberg picture, these are the states and this is the observable. In the Schrödinger picture, these are the states and this is the observable. So to distinguish the observable, I will write AS for A written in the Schrödinger picture, and so all this will be A in the Heisenberg picture. So this will be psi h and this will be psi s. So we can write this as psi t0h, ah, and psi t0h. To solve the time-dependent perturbation problem, these pictures are not good. We need another picture of quantum mechanics, which is the Dirac or interaction picture. So it is useful to apply this picture when we have a potential of this form, an Hamiltonian of this form, h0 independent of time plus a potential dependent on time, and so it is useful to solve our time perturbation, dependent time perturbation problem, and we will transform the states with a unitary transformation which is the time evolution, but not in h, but relative to h0. Okay. So we will apply u dagger to psi t. u to psi t0 and u dagger to psi t, and u dagger relative to h0, not to the whole Hamiltonian. So u dagger will take the simple exponential form a I h0 t divided by h bar, because h0 is time independent, so we can factorize the Schroedinger equation with h0 and we will have this simple time dependent factor. So this is u dagger of t. So I write the states in the Dirac notation with psi d and the states in the Schroedinger notation as psi s, and psi d is u dagger relative to h0 psi s, where dagger is the time evolution relative to h0, u is a time evolution relative to h0, u dagger is undoes that evolution, so it is this simple exponential because h0 is time independent. Psi s obeys the Schroedinger equation. Now I want to look for an equation, for a differential equation for the psi d. Psi s are governed by the Schroedinger equation, and psi d are governed by which equation? Now we will find out. So for psi s we have Schroedinger equation, I h bar time derivative equals h psi os. Instead, for psi d, let's see what we get in the right hand side. We use a chain rule, so and u dagger is the exponential, so we will do the derivative of the exponential, and then we do the derivative of psi s. So we get I h bar, derivative of exponential is I h0 divided by h bar times the exponential times psi s, and equal the exponential u dagger, and I times I is -1, h bar cancels out, so here we have minus h0. Now I use the Schroedinger equation to transform this term, so plus u dagger times the right hand side of the Schroedinger equation for psi s, and I get h psi s, but h I write it like h0 plus w, so I get this times s, and now we have minus h0 u dagger psi s plus u dagger h0 psi s plus u dagger w psi s. Now u dagger and h0 commute, because in u dagger we only have h0 in the exponential, so we can write this as h0 u dagger, and these two terms now cancel out, so we are left with u dagger w psi s. We want to find an equation for psi d, so we want to write psi s in terms of psi d and times, and if psi d is u dagger psi s is u psi d. So I write u psi d, and now we have our equation I h bar time derivative, and it is very similar to the Schroedinger equation for psi s. In fact, it is the Schroedinger equation for psi s, but instead of the Hamiltonian h, I have this, only this time dependent part written in the Heisenberg notation, right? Because this is the Heisenberg notation for w, but not with respect to the whole Hamiltonian h, but only respect to the Hamiltonian h0. So we have the Schroedinger equation with the Hamiltonian written in Heisenberg notation relative to the unperturbed part of the Hamiltonian. So W Heisenberg, let's say relative to H0. So we can now write this explicitly with the exponential, and we have the equation I h bar psi d on derivative on time exponential of I h0 t divided by h bar w exponential of minus I h0 t divided by h bar times psi d. Now let's take the time independent problem. A solution to that problem can be written as a state n, which is solution to this time independent Schroedinger equation. So the eigenstate n will have an eigenvalue En. Now let's take a set of n solutions to this unperturbed equation which are orthogonal. So let's take an orthogonal set of these solutions. Now to find a solution for psi d in this equation, we will write psi d in terms of this basis. So we will simply expand psi d like this, and obviously the coefficients will depend on time because psi d is the solution to the time dependent problem, but it can nevertheless be written as a linear combination of these states. It will simply evolve with time. So I have rewritten the equation for psi d here and the expansion for psi d here, and now we plug in the expansion to the equation and we get I h bar summation of the derivative in Cn, and the states do not depend on time, equals u dagger wu times the summation, I bring the summation here, Cn u dagger wu times the states n. Now on the left hand side I have an expansion in terms of n. Here I have an expansion in terms of u dagger wu n. I want to obtain an expansion in terms of n also here. So I will add here the identity matrix, which does nothing, so it will remain equal to this term, and I write the identity matrix with the completeness relation. So here I get the summation in M of this, and now I put this M inside here and I get the summation in n of Cn m u dagger w u n. Then I change name n with m. I do it here. Now I will do it here. N. So we also have an expansion in terms of n because these are scalar terms and I write them as kn. So we now have the summation of kn, kn n. So we have an expansion in terms of n in the left hand side and also in the right hand side. with Kn being equal to this, only to this part here. So term by term I must have IH bar derivative of psi n equal to Kn. So I have this differential equation for the coefficients. This can be written in matrix form as u dagger w u mm. So I get Kn equals the summation in m of Cm K n K, not K, u dagger w u n m. So the vector K is the matrix u dagger w u times the vector C, and we can therefore write IH bar derivative of the vector C equals the vector K, which is u dagger w u vector C. So this equation will give us the solution for the coefficients. Now writing again this as n u dagger w u m, and remembering that u dagger is this exponential and that the vectors, the states n and m, obey this time independent Schroedinger equation. We have that n u dagger is n times this exponential involving h0, so it becomes n times the exponential of I, and h0 becomes an t divided by h bar w exponential of I h m t divided by h bar. This time it's u and not u dagger times n. So we can take out these exponentials and we get exponential of I e n. Let's write e to the I e n minus e m t divided by h bar times n w m. Now a n minus a m divided by h bar is usually called frequency omega n m. So we can write this as e to the I omega n m t n w m. We write this in matrix index notation, and so we can write this differential equation in this form. Finally, we can write the solution in the Schroedinger picture, so we would get psi s, and psi d is u dagger psi s, so psi s is u psi d, the summation of Cn u n, and u is the exponential with h0 inside, so acting on n it will return the eigenvalue en, so we can write exponential of minus I en t divided by h bar n. So this is our solution in the Schroedinger picture, and the coefficients Cn will obey this equation. And this was the time-dependent perturbation theory. Pretty cool, right? So it's all for today. See you next time. It has been a pleasure.